Welcome everyone. Today we're tackling a really interesting problem called trapping rainwater 2. It's the three-dimensional cousin of the famous 1D version. Don't worry if it seems tricky at first, we're going to break it down step by step. So, what's the goal? We're given a 2D grid of numbers, where each number represents the height of a block of land. After it rains, we need to figure out how much water gets trapped between these blocks. Think of it like a landscape with hills and valleys, and we're calculating the volume of all the little ponds that form. Unlike the 1D version where water is trapped between two bars, here it's more complex. A cell can only trap water if it's completely surrounded by higher ground. The crucial idea to grasp is that the amount of water a cell can hold is limited by the lowest point on the wall that surrounds it. If you can find a path out that's lower than your current water level, the water will flow away. Let's look at the example. The cells on the very edge of the grid can't trap any water, right? Because any water there would just spill off the map. So you can think of this entire outer border as the initial seawall, or the initial boundary of our container. Now, if this wall were to break, where would it break first? At its lowest point, of course. This gives us a huge clue. We should probably focus on the lowest boundary cells first. Just a quick heads up. We'll be walking through the solution using Python. The logic, however, is the same for any language, so you can definitely follow along. So our strategy is going to be a type of breadth-first search, but with a twist. We'll start our search from all the border cells simultaneously. But instead of a regular queue, we'll use a Min-Heap, which is also called a priority queue. This is the magic ingredient. It ensures that we always explore from the current lowest point on our ever-changing seawall. It's like finding the weakest point in a dam, seeing what's behind it, and then rebuilding the dam to include the new area we've explored. First things first, we need to get set up. We'll create a visited grid, the same size as our map, to keep track of which cells we've already dealt with. Then, we create our Min-Heap. We'll kick things off by adding every single cell from the outer border into this heap. When we add them, we'll store their height, their row, and their column. And of course, we'll mark them as visited. Finally, we'll create a variable to hold our answer, the total water, and start it at 0. Now for the main part of the algorithm. We'll run a loop as long as there are still cells in our heap. In each step, we pop the cell with the absolute minimum height from the heap. This cell represents the lowest point on our current boundary. The height of this cell, let's call it current height, is super important. It effectively sets the water level for this step of our exploration. Once we have this lowest point, we'll look at its 4 direct neighbors. For each neighbor we find, we first check if we've visited it before. If we haven't, we can process it. First, mark it as visited so we don't come back to it. Now, the key calculation. How much water is trapped at this neighbor's location? It's the difference between our current water level, which is the current height we just popped, and the neighbor's own height. If the neighbor is taller, then no water is trapped, so we take the max of this difference and 0. We add this amount to our running total. Finally, and this is the most clever part, we add this neighbor to the heap to become part of our new, growing seawall. What's its height? It's the maximum of the current height and the neighbor's actual height. This ensures our wall only gets taller as we move inwards. Alright, here is the complete Python code for this approach. It might look a little dense at first, but it follows the exact logic we just discussed. Let's break it down into the key sections to make it clearer. This first part is just the setup. We get the dimensions of the grid, create our visited matrix full of false values, and initialize an empty list that will act as our Min-Heap. Then, we have a nested loop that iterates through every cell. The if condition here specifically checks if a cell is on any of the 4 borders. If it is, we push its height, row, and column into the heap and mark it as visited. Next, we initialize our total water and define a simple directions array to help us find neighbors easily. Then we start the main while loop. Inside, we pop the lowest height cell, which we just call height R and C. We then loop through our 4 directions to calculate the coordinates of the new row and new column for each neighbor. The if statement here is crucial. It makes sure the neighbor is actually within the grid boundaries and that we haven't visited it yet. And this is the heart of the solution, inside that neighbor loop. First, we calculate the trapped water. Remember, height is the wall we just came from, so we subtract the neighbor's height from it. We use max with 0 to handle cases where the neighbor is taller. We add this to our total. Then we mark the neighbor as visited. Finally, we calculate the new height for our wall, which is the maximum of the old wall and the neighbor's height, and push this new boundary point onto the heap. This little block of code does all the heavy lifting. So what about performance? For time complexity, every single one of the m by n cells will be pushed onto our heap and pop from it exactly 1 time. An operation on a heap of size k takes log k time. Since our heap can grow up to m times n elements, the total time complexity is on the order of m times n times log of m times n. For space, we need extra memory for our visited grid, and for the heap itself, both of which in the worst case can store information for all m by n cells. This gives us a space complexity of order of m times n. So to wrap it all up, what are the big ideas here? First, for problems like this, sometimes it's best to think from the outside in. The borders define your starting conditions. Second, whenever you hear a phrase like, always process the smallest, or find the weakest link, your mind should immediately think of a min-heap or a priority queue. It's the perfect tool for that job. And finally, the trickiest part was understanding how the seawall grows. The new wall's height is the maximum of the wall you came from, and the land you just stepped onto. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems, so if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. This channel doesn't make any money from sponsorships or ads yet, so if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.